Hello calculus fans. Today we are going to tackle part 2 of section 1110, which is dealing with Taylor and Maclaurin series. And we're just going to pick up where we left off on a handout. So here we are at example 6, and we are asked to find the Maclaurin series for e to the x. So what we typically do with these for Taylor or Maclaurin is we just start off writing down the function f of x equals e to the x. And then we just take some derivatives. So if you go f prime, f double prime, f triple prime. And then because it's Maclaurin, remember Maclaurin means that we're going to center this at x equals 0, right? X equals 0. So then I need to find f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. Okay, this one may be the easiest one in the history of Maclaurin series. Because if f of x is e to the x, what's f prime of x? E to the x. What about f double prime? E to the x and f triple prime, e to the x. Not a lot of changes here, not a lot of variety. So f of 0, so here's f of x, f of 0 is e to the 0, which of course is going to be 1. And likewise, all the rest of these are 1. Okay, so we know that for a Maclaurin series, it looks like this. F of x is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus, I'll go one more. Let's go f triple prime of 0 over 3 factorial times x cubed plus dot dot dot. Right? Goes on forever. Okay, so for us, we're using the Maclaurin series, we're going to say, so e to the x is equal to, well, f to the 0 is 1, plus f prime of 0 is also 1 times x is x. F double prime of 0, of course, these are all going to be 1, so 1 factorial, it'll be 1 over 2 factorial times x squared. So I'll just write it like this, all right, like x squared over 2 factorial plus, the next one is going to be x cubed over 3 factorial plus dot dot dot. So e to the x is kind of an easy one to see. It's just the pattern's really easy here. So if we wanted to write this, so remember this is expanded notation right here. If we wanted to use put it in sigma, using sigma notation, then we could say, e to the x equals, see, n equals 0 to infinity. So just looking at the pattern here, we basically got 2 factorial, so maybe 1 factorial, 0 factorial. So if I'm starting at 0, it looks like we could just have x to the n over n factorial, right? So let's just check. If I start plugging in 0, I want to see if we generate this. So I plug in 0, I get x to the 0 power, which is 1, 0 factorial. So remember, 0 factorial by definition is 1. So I get 1 over 1. Plug in a 1 here, I get x to the 1, which is x, over 1 factorial, which is 1. So we get these first two terms. And let's see, plug in a 2, we'll get x squared over 2 factorial, so it's working, right? So this is the expanded form, and this is just using sigma notation. Okay, so we've got that, and then example 7 is going to ask us to make use of this. It says find e correct to 4 decimal places. All right, so if you look at what we've got right here, we've got a formula for e to any power. So e would just be e to the first power. So you can basically just use this formula and put a 1 in for x, right? So it would be like e to the 1 equals 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial, right? So we can just use that. So let's see, let me move this up a little bit, and let's write it like that. Okay, so e to the 1, just using this formula, I'm going to plug in 1 for all the x's because e to the 1 is e. So we'll get 1 plus, 1 over 1 factorial. I guess, you know what, just to be, maybe I should have put that in there, 1 factorial, just to see the pattern more. Okay, so 1 over 1 factorial is just 1, plus 1 over 2 factorial, which 2 factorial is 2 times 1, which is 2, plus 1 over 3 factorial, so that's 6, but maybe I'll just start putting them in here now, plus 1 over 4 factorial, because when they get bigger, you know, not quite as easy to figure out, 5 factorial. So we need this to be accurate to 4 decimal places. So basically what we want to do is start plugging these in, and when the calculator stops changing at the 4th decimal place, we'll call it good, right? So let's see, 5 factorial is I think 120, so it's not going to be super small yet. Maybe I'll go one more. Okay, I'm going to go one more term. I'm going to go 1 over 6 factorial. Okay, so what I'm going to do right now, I'm just going to add these up and see what we get. Okay, so I'm just going to punch these in the calculator. And okay, so what I got when I added these up was 2.718056. You want this to be correct to 4 decimal places. So meaning when we round it to 4 decimal places. So right now, rounded to the 4th decimal place, I'd have to round that to a 1. But what we need to do is now see if I add another term, if it will change that, right? Because when it stops changing, when I add terms and it doesn't change to the 4th decimal place, then I'll know we've gone far enough. So let's add one more term. So if I add this term, then let's see what we would get. So I'm going to add all of these. So when I do that in the calculator, what I get is 2.718254. So to the 4th decimal place. Okay, it definitely changed, right? It definitely changed. So it looks like I'm going to need to add another term on here. So let's go plus 1 over 8 factorial. Now, of course, to really mean, if I'm really going to put an equal sign here, then we have to go forever, right? So I really need plus dot 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 if I'm really going to write equal. But for what we're going to do, we're just going to keep adding these until we get the 4th decimal place to not change anymore. So let's go and add this last one in there. And then if I do that, it looks like we're going to get 2.71828. Okay, so now at this point, it looks like we're locked in. So if we round, because remember, these are going to get smaller and smaller and smaller, and especially the factorials, because when you get much beyond here, they get big really quickly. So I have 1 divided by a really big number. So it looks like here, if I stopped here, I'd have to round this 4th decimal place to a 3, and here I'm still rounding it to a 3. So it looks like we're pretty safe to say that E rounded to the 4 decimal places is 2.7183. Okay, so hopefully that makes sense. It didn't really converge all that quickly. You know, that's kind of a lot of terms we had to add up right there. Some of them converge, oftentimes they converge a lot faster than that. But okay, so now we've got, I want to find the Maclaurin series for x squared e to the negative x. And this is much easier than it sounds because really we just need the Maclaurin series for e to the x, and we've already got it. So this is going to be much easier than you think. So let's just use what we already know. If you look at the previous problem, we figured out the Maclaurin series for e to the x, right? So e to the x is equal to the summation from 0 to infinity of x to the n over n factorial. Okay, and that's just from the example above. So if we wanted to change this to e to the negative x, it's very easy. I just have to change x here to negative x. Okay, so if I do that, we're going to get the summation from 0 to infinity. Instead of x to the n, I've got negative x to the n over n factorial. And typically when you have something like this with a negative in here, it's going to end up being an alternating series, so you typically want to pull this out. So think of that like this. Think of negative x to the n. Think of it like negative 1 times x to the n, right? And then if we've got two things multiplied together, both raised to a power, we can individually raise these to the power. So that's going to be the same as negative 1 to the n, x to the n. And that's what we're going to want to do here. And it makes it really easy to see then that this is an alternating series. Okay, so e to the x, we came up with this from scratch, but once we have it, it's easy to find e to the negative x. And then if we want x squared e to the negative x, that's also easy. I'm just going to multiply this thing by x squared. So then x squared e to the negative x is just going to be x squared times the summation that we had here, negative 1 to the n, x to the n, over n factorial. And now this x, because there's no n here, this can be moved right through the summation symbol, right? So we could bring this up over here. So really what we've got here is n equals 0 to infinity, negative 1 to the n, x to the n, over n factorial, and now times x squared, which means that these two will be multiplied together, right? Because x squared, you can think of x squared as just being x squared over 1. So then you can think of this just being a couple fractions I multiply together straight across. So when I multiply these, I'm going to add these, right? So I get n plus 2. So our final answer here for this would be the summation from 0 to infinity of negative 1 to the n, x to the n plus 2 over n factorial. Okay, so we can create these things from building from earlier from earlier series. Sometimes I think I talk too much. Get all tongue-tied. But okay, so that takes care of example 8. But don't worry, there's more examples. Look at example 9. Evaluate as an infinite series. Well, we multiplied a little bit last time to come up with that series. We had x squared e to the negative x. Looks like this time we need to divide. And when it comes to something like this, you can handle this a couple of ways. You could expand the series first and then integrate, or you could write it as a sigma notation first. So we'll look at both of them. Okay, I want to make sure we can do both of these. So what we'll do first, I'm just going to start off with sine of x over x. And I want to think of that as 1 over x times sine of x. Okay, and then we came up with a Maclaurin series for sine of x already, right? We came up with that earlier. So I'm just going to look back earlier in our notes. We came up with this as being 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So really all we're going to do with this, if you put this comes out here, we're going to multiply this by 1 over x, right? So if you think about if I were to move, so let's say just take this thing here. Whoops, I want to do that in red. So I take this thing here and move it over here. So it's 1 over x here, right? I'm just doing this to like save a step here. Well, this is 1 over x to the 1. So then this x will cancel. It will take one of these with it, right? Or you could do 2n plus 1 minus 1. But it's 2n. So this is going to cancel. I'll have x to the 2n left up here. All right. So basically what we'll have is this. The integral of sine x over x dx is equal to the integral of the sum from 0 to infinity of negative 1 to the n, x to the 2n, right? All over 2n plus 1 factorial. And again, all we did, we just canceled this x. We brought this x in front here, and then it canceled, so we get this. And then if we're going to integrate, of course, I need a dx. So we can integrate this in this notation that it's in this sigma notation, just by remembering that this is the variable here. This is the variable. And basically this whole thing right here will be treated like the constant. Right, so here's the constant, here's the variable. So when we integrate this with the power rule, this is our variable that will go up by 1, right? And we divide by this. Now, if you remember before in chapter 11 when we would have to find for like the ratio test a sub n plus 1, and we would swap n out with n plus 1, so we'd have to divide, we'd have to multiply the 2 through. Well, here it's not like that. When we integrate with the power rule, we just add 1, so it's just going to be 2n plus 1, right? So if we integrate here, just think if this were any other constant like 5. It just kind of goes along for the ride as we integrate. So this is going to go up by 1. The power goes up by 1, so it's going to be x to the 2n plus 1. Then we have to divide by 2n plus 1. Right? So what we get here when we integrate, we're going to get the series from 0 to infinity. We'll get negative 1 to the n, x to the 2n plus 1, divided by 2n plus 1 times 2n plus 1 factorial plus c. Right? So x to 2n is x to 2n plus 1. Then we have to divide that by that, which is right here. And here's the original 2n plus 1 factorial. Okay, so we can integrate an infinite series when it's in sigma notation like this, in the sigma notation. Or what we could do is expand first and then integrate, which is typically what we do, because normally we're doing this in some sort of applied setting. So this notation isn't, for most uses, isn't quite as helpful. But let's do this first. Let's do this. So I'll say or expand first, then integrate. All right, so what we'll do this time, we just expand this. So we'll start off, so sine of x over x is equal to 1 over x times the sine of x. And that is equal to 1 over x. I'm going to expand the sine. So remember, sine is all the odd powers. So you have x minus x cubed over 3 factorial plus x to the 5th over let's see if I can fix that. X to the 5th over 5 factorial plus or minus, oh my gosh, tore up here. Okay, minus x to the 7th over 7 factorial plus ... right? So then if this distributes through here, it's basically going to reduce each term, each power of x by 1, right, on each term. As this distributes through here, we get x times 1 over x, which is just 1. And then it'll come through here, and the x on the bottom will take out that x cubed, make it x squared. So basically we'll get this. We'll get 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus ... Right, so that is sine of x over x. And now if we want to integrate that, we can just say, all right, we're going to integrate sine of x over x dx, which means we're going to integrate that result that we just got there, 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus ... dx, right? So now we just integrate term by term. So the answer to this, well, the antiderivative of 1 is x. So I have an x here. Then I integrate here. This goes up by 1 to 3. Then I have to divide by 3. So I get minus x cubed. And then I get 3 times 3 factorial. Then I get plus x to the 5th over 5 times 5 factorial minus x to the 7th over 7 times 7 factorial plus ... And then, of course, at the end, we need a plus c. Okay. So that is how we can figure out these integrals as infinite series. All right, we've got yet another example. Hope you guys feel you're getting your money's worth with this handout, because this is a big handout. Lots of examples. So this one says they want us to show that when we integrate cosine of x dx, we get sine of x plus c. They want us to show this using series. Okay, so we could line up cosine of x like this. And we could say, okay, this is equal to, and I'm just going to do the expanded form of cosine. And we know this one. Remember, we did this one earlier. Cosine is all the even powers, so 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6 over 6 factorial, plus dot, 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 and then dx. Okay? So let's just integrate term by term. All right, just basically we know the antiderivative of 1 is x, and then we use the power rule on all of these. So it's a really easy integral. So you get x minus x cubed over 3 times 2 factorial, plus x to the 5th over 5 times 4 factorial, minus x to the 7th over 7 times 6 factorial, plus dot, dot, dot. And then, of course, we've got a plus c, because this is an indefinite integral. So the answer is going to be a function plus c, right? If it were a definite integral, then we wouldn't put the plus c. We would put the solid line here, put the limits of integration, and then the next step we'd plug those in, just like the fundamental theorem of calculus says we can do. And then we can actually clean this up a little bit, because isn't it true that 3 times 2 factorial, isn't that just 3 factorial? And 5 times 4 factorial, that's just 5 factorial. So we could actually write this as x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus dot, 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 plus c. And if you look closely, you might recognize that also from the other day. That is just the series expansion for sine of x plus c. Okay, so we knew this was true from before, and this is just a verification using infinite series. Now, I know you're probably thinking at this point, I wonder if we could multiply and divide these power series. Oh, look at this. Look at that. Bit of a mind reader, I know. But yes, we can, in fact, multiply and divide these power series. So we've got an example right here we can take a look at. All right, so this one, if you look closely, we're going to first multiply, because this is e to the x times cosine of x, right? We're going to multiply. So I'll put a little dot here to make it easy to see. Okay, e to the x times cosine of x. So the way we do this is we just set this up over here. So I have e to the x times cosine of x. And what I'm going to do is line up the series expansions for this one, and then we'll start to multiply. So we can do it like this. So e to the x, we know this one because we actually found both of these. So this is going to be x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And then you want the first 3 non-zero terms. I'm going to go one more, plus x to the 4th over 4 factorial, plus dot, dot, dot. And then I multiply by cosine. Okay, so cosine of x is 1. Let's see, 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus dot, dot, dot. So when we multiply these, we just have to make sure we distribute correctly. So I'm just going to start with this 1 and distribute this all the way through. So it'll be 1 times 1, 1 times negative x squared over 2 factorial, 1 times x to the 4th over 4 factorial, and so forth. Then I'm going to go here. Now we only need the first 3 non-zero terms, so I don't have to do this forever. So then I'll do the second term and distribute that through, right? We'll just keep on doing that till it looks like we've got enough terms. Okay, so let's start right here. Okay, I'm going to start, and I'm just going to take 1 and I'm going to multiply it through here, and then here, here, and here. And 1 times that, as you know, is just going to be that, right? It's not going to change anything. So that would be 1. Now I'm going to leave a space because when I multiply this second one, there's an x squared, but I'm going to leave a space here for the x term because there are possibly going to be, you know, x terms and things and x cubed. So I'm going to leave a little space here. So I'm going to go 1 times 1 is 1. 1 times negative x squared over 2 factorial is negative. I'm just going to write it x squared over 2 because we may have to add these or combine these. And 2 factorial is just 2, right? Okay, then the next term is x to the 4th over 4 factorial. So I'm going to leave a space again in case there's a cubic term. Go x to the 4th over 4 factorial. And it's probably far enough. We need the first 3 non-zero terms. So I'll stop there. If we have to go further, I will, because it could be that some things are going to cancel. But that's probably good for now. Okay, now I'm going to take the second one. I'll use a different color here. So now I'm going to take this second term and distribute that through. So it'll go here, 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 and I probably won't go all the way over here again. But okay, so let's see. So first, when I multiply this by 1, of course, it just shows up. So it's just going to be x over 1 factorial, which is just x. So I'm just going to put an x here, right? So this is x over 1 factorial, which is just x times 1. Then I come over here, I have x over 1 factorial, which is just x, and I multiply by this, so that's going to give me minus x cubed over 2 factorial. Minus x cubed and 2 factorial is just 2. And then, let's see, then we've got one more, maybe we'll do, so this will give me x to the 5th over 4 factorial. So I go plus x to the 5th over 4 factorial. Okay. And then let's see, the next one we've got is this one. So let's try a different color here. We'll go this here and then here. And yeah, that's probably as far as we need to go. Because if I go to this one, now I've got x to the 6th, right? So I'm not going to do that. I'm just going to do the first 2. All right, so this times 1 is just x squared over 2 factorial, which is x squared over 2. And that's a positive. So we can already see this is going to cancel, right? Those two are going to cancel out. Okay, so then I go to the next one. I'm going to go x squared over 2 factorial times x squared over 2 factorial. Well, that's going to be x to the 4th over 4, right? So that'll be x to the 4th over 2 factorial times 2 factorial, which is just 4. Now these two, of course, won't cancel because they're both... Oh, wait a second. That is a negative, isn't it? Sorry, that's a negative. Because I've got x squared over 2 factorial times negative x squared over 2 factorial, so it's a negative. These don't cancel because this is 4 factorial, right? 4 factorial is actually 24. But we can see at this point we can stop. We can stop here because we need the first 3 terms. Let's see, this is x cubed. Okay, well, we better do one. We got to do one more, right? Because this is x cubed. So we've got 1, 2. These are going to be canceled, so we're going to have an x cubed. So we better do one more. So let's do this one. Do this one with red again. So this is going to go through here and here. So when I multiply here, I get x cubed over 3 factorial times 1. Okay, so that is going to be x cubed over 3 factorial. So 3 factorial, that's 3 times 2 times 1, which is 6. Okay, and then the next one would be over here, which would be x cubed times x squared, which is x to the 5th. But I definitely don't need that one. We just need the first 3 terms, right? First 3 terms. So I don't even need to add that one up. because when we add these, now we're going to get, this is going to be equal to 1 plus x. These two cancel. But if you need the first three non-zero terms, now we just need to add this and we'll have all we need. So x cubed over 6, this is negative x cubed over 2. But what I could do is multiply this by 3 over 3, right? And then we would get negative 3x cubed over 6 plus x cubed over 6, which would be negative 2x cubed over 6, right? Negative 2x cubed over 6 is just negative x cubed over 3. So you get negative x cubed over 3, and then we just go plus dot, dot, dot. All right, they just wanted the first three terms. This is the first three. Now it keeps going, but we just need the first three non-zero terms, so this is it. Okay, so multiplying is a little bit of work. Just have to be careful. Make sure you go far enough so that if anything cancels, you still have enough terms, and we don't leave anything out. But we can do something like that. So that's multiplying, but I know if we didn't do a division problem, you guys would be very disappointed. So look at this one. We've got division. Also might even notice something about this example. Okay, for those of you who remember some trig, what is sine over cosine? Tangent, right? This is tangent. So we're going to basically find the Maclaurin series for tangent. We're going to find it by dividing two series that we already know. Okay, this is a little bit of work too. But we know this because we know that sine of x over cosine of x, we already found the Maclaurin series for these earlier. For sine, it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. And for cosine, all the evens, right? Whoops, it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. So then we just have to divide like normal, right? So when you divide sine divided by cosine, this comes out in the front, right? This comes out in the front. So this is going to come out in the front. So what we'll get is this. This is going to look like so much fun when you see it. Get 1 minus... maybe I'm going to write it like this so that it'll be easier to work with. I'm going to pull out the coefficients in front. So 2 factorial is 2, so I'm going to have x squared plus 4 factorial is 24, so I'm going to have 1 over 24 x to the 4th minus dot, dot, dot. And then we've got our division. And okay, then, so this comes out in the front, so now this is going to be under here. And once again, I'm trying to make this easier by pulling out the coefficients in front. So 3 factorial is 6, so it'll be negative 16x cubed. 5 factorial is 120. So 5 factorial, it's just 5 times 4 times 3 times 2 times 1. That's 120. So we get plus 1 over 120 x to the 5th minus dot, dot, dot. But again, we just want the first 3 non-zero terms, so we don't have to go forever. So this should be far enough for what we need. All right, so what I need to do is think, what can I put here that I'm going to multiply this by to turn that into x? And it's going to have to be x, right? Going to have to be x. So if I put an x here, then I'm going to multiply this whole thing, all 3 terms, by x and line them up under here. So when I multiply by x, I get x minus 1/2 x cubed plus 1 over 24 x to the 5th. Then, of course, what we do is we subtract. So, and you subtract all of these. So basically all the signs change, right? So this becomes a negative. This becomes a positive. This becomes a negative, right? Because the signs all change because we subtract. So that goes. And now we're going to have, we've got negative 1/6 plus 1/2. Okay, negative 1/6 plus 1/2. Well, this is 3/6, right? So negative 1/6 plus 3/6 is 2/6, or 1/3. So we get 1/3 x cubed, and that's positive. Okay, then over here, we have to combine these. So we've got 1 over 120, 1 over 120. 1 over 24, if I multiply that by 5, I'll get 5 over 120. Of course, this is a negative, so that gives us, what, negative 4 over 120. Negative 4 over 120 is negative 1 over 30. That would be x to the 5th. Okay, so then, of course, this... Whoa, okay. So come on, software. Work with me here. Plus dot, dot, dot. Okay, so then we have to think... Okay, I've got to now multiply something by this to turn it into an x cubed, right? I need to work on this over here. So what could I multiply this thing by to turn it into a 1/3 x cubed? Well, I've already got, it's just a 1, so it's going to just be 1/3 x cubed, right? So I go plus 1/3 x cubed, because remember, we're trying to turn this first leading term here into that thing. Just like we did here, we turned it first into an x by multiplying by x. So now we need to turn it, it's kind of it's easy to do when the lead term is 1, right? It makes it a little easier. But to turn the lead term into this, we just multiply by that. So I'm going to multiply all 3 terms by 1/3 x cubed. When we do that, we will get 1/3 x cubed. And then that would be minus 1/6 x to the 5th plus dot, dot, dot. We don't need to go any further. And then, as usual, we subtract. So I'm going to go minus here. This will end up being a plus because all the signs change. That's gone. And when we add this, negative 1/30. Now, this is the same as 5/30, right? So it would be 4/30 or 2/15. So when we add these, we get 2/15 x to the 5th plus dot, dot, dot. And now we need the third term, so we got one more to go. And we just need to think, what do I put here that I multiplied this by to turn it into this? And that one's pretty easy. It's going to be plus 2/15 x to the 5th. And we can just say plus dot, 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 right? It keeps on going. But we just need the first 3 non-zero terms. So that's it. So the Maclaurin series expansion for tangent looks like this. If we wanted to find a pattern, we just have to go a little further, right? But they just need the first 3 terms, so this is what we get. All right, so we got example 13 here. A little note here. The note is there is no closed form. We just say no closed form antiderivative exists. Or in other words, we can't express the antiderivative of this function in terms of the elementary functions, which is basically every function that you've ever seen, right? Every function you've ever seen all the way up to Calc 2. So that means we need to use some sort of approximation technique, right? We can't use the fundamental theorem of calculus to get the exact value because the fundamental theorem of calculus says evaluate the antiderivative of this at 1 and at 0. We can't evaluate the antiderivative if it doesn't exist. So we're going to need some approximation technique. And I guess we could probably try to use, I don't know, maybe Maclaurin Series expansion? Let's try that. Let's try that because we know cosine of x. So if we know cosine of x, we can build this from that. All right, so let's build this series, and then we'll just evaluate term by term. It'll be pretty easy. All right, so to build up the series, we start with what we know. We know cosine of x. We know that cosine of x looks like this. It's all the even terms, right? Even powered terms. We'll go one more. right, so that's cosine of x. So if I have 1 minus cosine of x, what that means is 1 minus all of this stuff, right? 1 minus this. One minus all of that. So if I distribute this negative through, I'm going to get 1 minus 1. So the 1's completely cancel. And then don't all these just swap signs? So what we get for 1 minus cosine x, we're going to end up getting x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus x to the 8th over 8 factorial plus dot, dot, dot. Okay, so continuing, if we have 1 minus cosine of x over x squared, well, all I'm going to have to do, I mean, you could think of it as like this, 1 over x squared times cosine of x. All that means is we're going to distribute this 1 over x squared through this whole line here, right? So it's going to basically just knock down each power by 2, right? So if I multiply 1 over x squared here, the x squareds cancel, I get 1 over 2 factorial. Over here, the x squared would make that x fourth become x squared. All right, so basically knock off x squared from each of these terms. We'll get 1 over 2 factorial minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6th over 8 factorial plus dot, dot, dot. And once we've got this, we're ready. We're ready to integrate now. So to integrate this one, we can say that the integral from 0 to 1 of 1 minus cosine of x over x squared dx is equal to the integral from 0 to 1. Now I'm just going to copy this function down, or this series. So I have 1 over 2 factorial minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6th over 8 factorial plus dot, dot, dot dx. All right, as long as we know how to do the power rule for integration, we can integrate this function. Okay, this is just a constant, right? This is just 1/2. The antiderivative of 1/2 is 1/2 x, right? I'm just going to put the x's on top, though, just to be consistent. So I'm going to write it like this, right? So keep the factorial just to be consistent with the rest of them. But this is just going to be, when I integrate this, I get this times x, which I could write this way. And then we get minus x cubed over 3 times 4 factorial plus x to the 5th over 5 times 6 factorial minus x to the 7th over 7 times 8 factorial plus dot, dot, dot. We evaluate from 0 to 1. So hopefully this makes sense for just using the power rule. So in this case, this 4 becomes a 5, then I divide by 5. So it's like this. Now you can see over here, I basically just need to put a 1 in here, because the 0, when I plug the 0 in, they all just get wiped out. So we really just need to plug the 1 in here and see what we get. Okay, so if I plug in a 1, we get 1 over 2 factorial minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial minus 1 over 7 times 8 factorial. And then it keeps going, of course, if I want the exact answer. But just to get an approximation, let's see how close we are. Okay, I just want to add together these 4 terms, which is definitely an approximation, right? Because to get the true answer, to get the exact answer, I would have an infinite number of terms here, right? This is an infinite series. But in practice, what we do is we just get an answer that's good enough. Like maybe we need an answer to 4 decimal places or so. So for this one, I just want to see how close this is. So I'm just going to punch this in the calculator. Okay, so when I did this, I got This equals 0.48638534558. Just to check, I just punched in the original problem into the TI-84. And of course, it uses an approximation technique, which I may have mentioned before. It uses what's called the Cordic algorithm. And what it gets is 0.48638535762. And this one should be accurate to this decimal place, right? So we stopped here after only 4 terms. So ours is not going to be quite as good as the calculators, but we could, right? If we add another term or two, we'll be agreeing with it here. But not bad for only 4 terms. Plus, it's easy to see the pattern here, right? If you needed to throw another term on here, I don't really need to do more work. Can you see that it's going to be, first it's alternating, so you're going to have a plus, and then look at the pattern 5, 6, 7, 8. So it's going to be 9 times 10 factorial, right? So it's pretty easy to see the pattern. All right, so this next example wants us to find a Taylor series. So remember, Maclaurin series is just a special case of the Taylor series where we center it at 0. But now we're going to, instead of centering at 0, we're going to center this at a equals pi over 2. All right, so we do this the same as always. We start off with f of x, and we need some derivatives. Now this one is also going to be one of those that we're going to need a lot of them because we're centering this at pi over 2 when cosine of pi over 2 is always 0, right? So we're going to need quite a few of these. So let's do it like this. We'll figure out these values, and then we'll figure out these values at pi over 2. F prime of pi over 2, f double prime of pi over 2, f triple prime of pi over 2. And then we'll start over here. We'll do this again, okay? Because a lot of these are going to go away. Just like when we did sine and cosine with Maclaurin series, a lot of them canceled. We're in the same boat here because of pi over 2. If I didn't pick 0 or pi over 2, we wouldn't have this, but we're going to need to just make some more derivatives. So let's go to the 4th derivative of x, the 5th derivative of x, the 6th derivative, and I think with the 7th derivative we should be good. And then, of course, we need to plug in pi over 2 at all these points. So we have to the 4th derivative of f of pi over 2, then the 5th derivative of the function at pi over 2, 6th derivative, and finally the 7th derivative at pi over 2. All right, so f of x is sine of x. Okay, you should press pause and quickly fill all of these in. You still here? You didn't press pause. Press pause. All right, hopefully press pause. So if we keep going, we'll get cosine of x, and then negative sine of x, and then negative cosine of x, which brings us back to sine of x, and then cosine of x, negative sine of x, and negative cosine of x. Okay, I think we've got it. Now we just have to fill these in. So just real quick review here. The sine function, here's pi, here's 2 pi. Sine goes like this, right? Here's pi over 2 right there. Cosine, of course, goes like this, right? There's basically a shift of pi over 2. So this is pi over 2 right there. So if we fill these in, sine of, well, we can fill all the cosine ones in easy, right? All the cosine ones get 0, 0, 0. Sine of pi over 2 is 1. Negative sine of pi over 2 is negative 1. Sine of pi over 2 is 1. Negative sine of pi over 2 is negative 1. All right, so when we're using Taylor series, we know f of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. Right, so it looks like Maclaurin, like we've been using, but Maclaurin would be, the inputs would all be 0, and this would just be x, because the a would be 0, and this would be x squared. But other than that, they're pretty similar. So f triple prime of a over 3 factorial times x minus a cubed plus dot dot dot, right? So that's the Maclaurin series expansion. So for us, we've got sine of x is equal to f of a. Okay, f of a is pi over 2. All right, so f of a is pi over 2. F of a is 1. And you can see like what's going to happen here. The prime, f prime of a is 0. F triple prime of a is 0. So the triple one will be gone. So what we'll have is f of a is going to be 1. And then the next one that comes up is going to be, since this will be 0, f prime of a is 0, so this one's going to be 0. And the triple third derivative will be 0. But we'll have this one right here is a -1. So we'll have -1 times x minus a squared over 2 factorial. So it's going to be basically minus x minus pi over 2 squared over 2 factorial. And then we will have this third f triple prime of pi over 2 is going to be 0. But then the fourth one is a 1 again. So we're going to have 1. So it'll be plus 1 times x minus pi over 2 to the 4th power over 4 factorial, right? Because that would be the next one in the line here would be the 1. And then, again, the 5th derivative will be 0. Then the 6th derivative is a -1. This would be the 6th. So the next one that would come up here would be minus x minus pi over 2 to the 6th power over 6 factorial plus. And at this point, you can see there's the pattern here, right? So we have this pattern established. So this is basically the first 4 non-zero terms. And of course, this goes on forever. And I can put the equal sign as long as I put plus dot dot dot, right? If I just put these first 4 terms, it's an approximation. But Taylor series, as long as we have the infinite series expansion, it's exactly the same as sine of x. And then if we wanted sigma notation, we could also write that. So if we have sigma notation, we could say sine of x is equal to n equals 0 to infinity. Well, notice it's an alternating series, so we're going to have -1 to the n. And then the denominator's all even powers, right? Or I'm sorry, are even factorial, so it's going to be 2n factorial. And then we have x minus pi over 2. And these powers are all even, so it's 2n, right? So this would be sigma notation, of course. And then this is just the expanded form. Okay, now they do ask us to find the associated radius of convergence. So we've got the Taylor series centered at pi over 2. And then to find the radius of convergence, okay, this is just, we can just use the ratio test again. And we use a ratio test with this, with our sigma notation. So let's try this out. So the radius of convergence which is, of course, means we're going to use the ratio test. So the limit is n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And that's absolute value. That's going to be the limit as n approaches infinity of, let's see, this would be -1 to the n plus 1 times x minus pi halves to the 2n plus 2, right? 2n plus 2, because this n gets swapped out with an n plus 1. So you have 2 times n plus 1, which is 2n plus 2. Okay, and then let's see, the bottom would be 2n plus 2 factorial. The same reason, this n becomes n plus 1, then we have to multiply it by 2. Okay, then we're going to multiply by the reciprocal, right? So we're going to multiply by a sub n, which is like, or we're going to divide by a sub n, which is the same as multiplying by the reciprocal. So that means we're going to multiply by 2n factorial. Then we'll have -1 to the n, and then x minus pi over 2 to the 2n, absolute value. Okay, so the negative ones are going to go. They're in absolute value, so we don't have to really worry about them. They're going to be gone. And then we're going to have, all right, so 2n plus 2 factorial. That's the same as 2n plus 2. Then you walk it back by 1. It'd be 2n plus 1, right? Walk it back by 1. It's 2n. And then I can stop right there and just leave it at 2n factorial, right? So that takes care. This is just the expanded, a little bit expanded version of this. And now we can cancel the 2n factorials. Then we've got something else that can cancel. There are 2n plus 2, there's this to the 2n plus 2 power in the numerator, and this to the 2n power down here. So 2n plus 2 minus 2n is just 2. So basically, that will go away, and this will just be that squared. So what we'll have then here is, let's see, this will be the limit as n approaches infinity. And we'll have, I guess we don't need any absolute values because on the top we've got x minus pi over 2, and it's squared anyway, so it's going to be positive. And down here we've got 2n plus 2 times 2n plus 1. And when we take the limit of this, and as the denominator goes towards infinity, and this thing is just x minus pi over 2 squared, the limit of this is going to be 0 because the denominators grow without bound. So the limit of this is 0, which is less than 1 for all x. So the radius of convergence is infinity, right? Okay. So what I'm going to do, I just want to get an idea of how good this approximation is. So what this approximation is the approximation of sine of x centered at pi over 2. So I'm going to take the graphing calculator and I'm going to graph the function, the sine function, and I'm also going to graph this function so we can take a look and see how they look. So our two functions are here, and y1 is the sine, and then y2 is our Taylor series approximation centered at pi over 2. So I'm going to hit zoom 7 to set the window so it'll zoom for trig. So here's our sine curve, and now our approximating curve will be coming right here, and this one is centered at pi over 2, and you can see it's a pretty good approximation. Last thing I wanted us to try is just want to try a problem here. So let's say we had to estimate the square root of 10. When I estimate the square root of 10, and they say to use using a third degree, or we'll say, let me say a third order, which means the same thing, by the way. Third order Taylor polynomial. Okay, so basically it's going to be a cubic approximation. So we're going to have a third degree polynomial approximation for the square root of 10. So this is kind of how you go about this kind of problem. All right, so we start off, it's a square root of 10. So the function we're going to use is the square root function, right? We're going to use the square root of x for our function because we want the square root of 10. And then our a value would be 9, right? So we're going to center this at 9. So we'll say f of x equals square root of x and a equals 9. So this is kind of the starting point here. Now I want to use 9 because 9 is the square root that we know the answer to, and it's close to 10. All right, so if they asked me to approximate the square root of, say, 28, I wouldn't use 9 then, I would use 25. Because remember, this is where we're going to center our polynomial at. It's where we're going to center it right at 9, which is close to the square root of 10, and we know the answer to the square root of 9. So that's why you want to think about these things. Then we just need a few derivatives. So we've got f of x, of course, is the square root of x, which I'm going to write it as x to the 1/2, because then it's easier to take the derivative. So then the derivative would be 1/2 x to the negative 1/2. And I'm going to also write it like this, 1/2 times the square root of x, right? The reason I'm writing it like this is because we're going to have to plug in values to solve these. So this is a little bit trickier, but x to the negative 1/2, isn't that just 1/x to the positive 1/2? And 1/x to the positive 1/2 is 1 over the square root of x, right? And then the 1/2 times that. Okay, so we need the second derivative, which is going to be the power rule here. So we get negative 1/4 when I multiply. Negative 1/4 x to the minus 1/2 minus 1, which would be minus 3/2. And again, because we're going to have to figure this out when we plug in our a value, I'm going to write this in a way that we can actually work with it a little bit. So it's like a negative 1/4x to the positive 3/2. And then let's do one more, the triple prime. So here we do the power rule, so we multiply, so we're going to get negative times negative is positive, so we get 3/8. X to the minus 3/2 minus 1, which is minus 5/2. And one more time, I'll do it like this, 3/8 to 3/8x to the positive 5/2. Okay. All right, that does not look like 5/2 very well, so let me do this a little bit better, to the 5/2. Okay. Because then we need to figure out all of these things at 9. So f of 9 is just the square root of 9, right? X to the 1/2, square root of 9. So that's going to be 3. We need f prime of 9. Well, f prime of 9 is going to be 1/2 times the square root of 3, or times the square root of 9, right? Which is 1/2 times 3, which is 1/6. And then over here, I'm going to have to plug in 9 here and 9 here. So remember, 9 to the 3/2, 9 to the 3/2 is just 9 to the 2/2 times 9 to the 1/2, right? 9 to the 2/2 is just 9. 9 to the 1/2 is the square root of 9. So this is going to be 9 times 3, which is 27. So then we're going to have f double prime of 9 equals negative 1. And then 4 times 27, which gives us negative 1/108. Okay, and then finally we're going to have to figure out 9 to the 5/2. We can do that just like we did here. So 9 to the 5/2. You can do this another way too. So see how when I did this 9 to the 3/2, I could have went, that's 9 to the 1/2 cubed. I could have went 9 to the 1/2 cubed, right? Because then you multiply. And then we would get 9 to the 1/2 is square root of 9, that's 3. 3 cubed is 27, so it works the same way. So you can do this either way also. But I'll say 9 to the 4/2 times 9 to the 1/2. So I'm going to make this the highest integer power I can and then leave it here. So This means this is like 9 squared, which is 81 times 3, right? So this is 81 times 3, which is 243. Now, I guess you could just punch this in the calculator too. Maybe that'd even be easier, but I know you guys probably like more of a challenge. So, okay, so we're going to get down here. This is going to be 3 times 8 times 243. And now 3 goes in here once, goes in here 81 times. So we end up with 1 over 648. Okay, a lot of arithmetic here. But now we are ready to put all the pieces together. We've done the work. So now we can say, okay, so f of x, our function, is the square root of x. And we know that it's approximately equal to, excuse me, f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared, and then plus f triple prime of a over 3 factorial times x minus a cubed, because we're doing the third degree, right, or third order Taylor polynomial. So we get square root of x is approximately equal to, well, f of a, that's 3. So this is going to be 3 plus f prime of a, which is 1/6, times x minus a. Now it's really easy to mess up this x minus a. A is 9, right? 9. It's not 3. It's super easy because we take the square root of it. It's so easy. It's the most common mistake of all is probably to put a 3 here. But you know when you do that because you get weird answers that don't make sense. It's a. Just look at the formula. A. That's where we're centered at. A, right? So a is 9. Okay, so then we go over here and we've got f double prime of a, which is a negative. So we've got negative 1 over 108, and I have to divide that by 2. So divided by 2 is like multiplying by 1/2, so I basically double that. So that's going to give us minus 1 over 216 times x minus 9 squared plus, and this is where we need a calculator, right? F triple prime of a is 1 over 648. That's I didn't really write this one out, did I? I did f double prime of 9, and I just kind of threw in the number here. It's not really equals. What this should say is f triple prime of a equals. Okay, but anyway, it's 1 over 648. Then we have to divide that by 6, right? So I had to do this one, did this in the calculator real quick, and what I got was 1 over 3,888 x minus 9 cubed. So this is our Taylor series approximation for the square root of x centered at 9, right? This is for one centered at 9. So if we're around 9, we might get a decent approximation. And we wanted to approximate the square root of 10, so we're close to 9. So we should get a decent approximation. So let's see what we get. Using this one, we'll say the square root of 10 is approximately equal to 3 plus. Now all I'm going to do is plug in 10 for all the x's, right? Plug in a 10, a 10, and a 10. So this one ends up being kind of easy. We're going to get 1/6 because 10 times 9 is 1. Minus 1 over 216. 10 times 9 squared is 1 squared. 1 over 3888 because 10 minus 9. Again, I plug a 10 in here. 10 minus 9 is just 1 cubed is just 1. Okay, so when you fill all this, or plug all this in the calculator, we get the square root of 10 is approximately equal to 3.162294239. Now, just to see how close we are, this is on the calculator, the TI 8384, using its approximation technique, the Cordic algorithm. What it gets is 3.162277766. So we agree to about right there. Okay, now this one should be accurate to this last decimal place because that algorithm goes on further. We just have a third degree, right? We're approximating this with a cubic. So if we wanted more accuracy, we could just add on more terms, right? And if we added on enough terms, we could get as accurate as we want. Because if we went to infinity, then we would get the exact answer, right? So that's just an example of one, just so you can see how they work. And now you've seen, I think, everything you'll need to take care of the homework in section 11.10. So give it a try, and of course, let me know if you run into any trouble.